different. And I also agree with you that if I was going at this via geometric quantization, I would use the compact forms of these groups to try to get at it. But the truth of the matter is that the analytic end of the theory falls far short of what can be done combinatorially. I guess my actual focus in my own research is that there's a more sensitive theory that underlies all of this, that takes into account representation of the fundamental group of the a particular representation of the fundamental group of the complement of the knot into SL2C, and then there is a Jones polynomial-like object. It's not a polynomial anymore. It's a series that depends on which representation, and so what you get is you get a meromorphic section of the character variety of the knot complement then, and that's quantum type theory. And I guess, you know, in my mind, I just think about SL2C anymore. So, but you're absolutely right that the analytic attempts to understand this all involve the compact forms of groups. Okay, so now suppose, you know, S3 minus K is hyperbolic. And that means, in fact, that you can realize the universal cover of S3 minus K as hyperbolic 3 space. And then you have a homomorphism from pi 1 of S3 minus K into SL2C, whose image, the image of rho, is a discrete finite covolume subgroup. Okay.
So
And now, yes?
I always get confused by this point, but is it, so there's a homomorphism to PSL2C, but does it always lift?
It always lifts, and the reason is that 3 manifolds are parallelizable. And in fact, if the second homology of your 3 manifold is non-trivial, then there's more than one lift, and the lifts correspond to spin structures which are in a fine space over the second homology.
I see. So
But for a knot complement, there's nothing there.
But for hyperbolic 3 manifolds, it always lifts. Right?
It always lifts. Always lifts. In fact, yeah. You can find that proof that it always lifts in Thurston's notes if you go find his 1976 notes. Okay. Now, you know, probably the best thing to do is to work with an ideal triangulation, or work with, you know, a decomposition as a 2 complex, you know, because in fact S3 minus K is homotopy equivalent to a finite 2 complex, and that's probably the best way to proceed. And so you find a CW decomposition here, and then you lift that CW decomposition up to the cover, and what you get then is, you know, C2 of S3 minus K, well, Ci of S3 minus K is a free, oh boy, Ci1 of S3 minus K.
Are you taking Ci of the hyperbolic 3 space or something?
Say it again?
Well, that's the chain complex associated to S3.
Yeah, so what I really have here is living in here, I have a chain complex, and then living over here, I have a chain complex. And I just construct this chain complex.
I'm just wondering, when you write Ci of S3 minus K, is that what you're going to have
Yeah.
a fundamental group on the chains of
You're right. I'm so sorry. I told you it was going to get looser.
That's fine.
It's loose.
That's fine, no problem.
Are we good?
Yeah.
So we can form this chain complex, and then what we do is we can tensor this over I1 of S3 minus K, like that. And now we've got a regular old vanilla chain complex defined over the complex numbers. Okay. And then what we can do is we can calculate its torsion.
You're tensoring through row, right?
Say it again?
You're tensoring using row, is that right?
Yes.
Yeah.
So here it acts as deck transformations via row. I mean, as deck transformations, and here it acts via row. And so what I'm saying is, if I have sigma deck transformation of gamma tensor of vector minus sigma tensor row of gamma on vector. And this is an acyclic chain complex. And so then you can calculate its torsion. So here is, why don't we call this TI C of X2? Because now what I'm going to do is I'm going to iterate the procedure. So
This is as a, for the group ring of the entire fundamental group, or
the group ring of the entire fundamental group, which by the way is the same as gamma, but once I've done this, it just, once there's a right module and a left module, now it's just over the complex numbers, and so there is torsion defined. This actual torsion that he studies first appeared in Dennis Johnson's notes on the geometric Cassins invariant. It's the last section. This is the torsion that he studied.
Did you say you assume this is acyclic?
It is acyclic. I don't need to assume it.
But that must depend on row, doesn't it?
It depends on the fact that,
it's discrete.
that it's discrete.
But you could have a trivial factor for them.
You don't, because it's irreducible. There's no really.
Oh, the image is discrete.
Yeah.
The image is a lattice. That's what
Yes.
Okay.
The image is a lattice.
That's fine.
But now the idea is that you take the polynomial representation, pi 1 of S3 minus K to SL2C, and then you do the same thing you do with the colored Jones polynomial. So now you just follow it up by the irreducible representation into here, and then you can form the chain complex Ci x tilde tensor pi 1 of S3 minus K over Cn, and then you can calculate the torsion of this chain complex. And now we have to do this for n odd, it turns out. And so now we're taking tau of Ci of xn divided by tau of Ci of x2. And then we take the limit as n goes to infinity of that, but I'm a little worried. I think I also have to divide by n squared. And what you get is negative the volume of S3 minus K over 4 pi. So in fact, the volume conjecture has been proved for Reidemeister torsion when you color the chain complex with each one of the irreducible representations of SL2C. It's a 2014 paper. So it seems to me that the negative sign is because you were looking at the wrong chain complex. You should have looked at because it's shrinking, you should have looked at the dual chain complex. Who knows where the extra 2 comes from and why it's the n squared, but maybe this is because of the way Reidemeister torsion shows up in the asymptotics of the colored Jones polynomial, because I think it shows up as like a square root or something like that. But in my humble opinion, I think that the volume conjecture is going to turn out to be a corollary of this. That's what I think. Which is, there you go.
Sorry, so there's a silly question there. When you talk about the CW decomposition of S3 minus K,
Yeah.
you first think of S3 minus K as a manifold with boundary? Is that what you're saying?
No, deformation retracts onto a spine. That's a spine.
Oh, I see. You first
Just
replace
take
it by
a
its
spine.
spine. Okay,
Yeah.
I see. But I could do it with boundary, right?
Yeah, you could do it with boundary. So, we done with this bit of the story and I can tell you more outrageous lies?
One question.
Yeah.
Continue on this. If you look at the representations of the knot group, the SU2,
Yes.
I guess.
I wrote a paper about that.
Yeah, and what does that, what kind of space do you get? I mean, just getting one isn't that hard.
You get a bunch of arcs, and with singularities, and that's because of Poincare duality. You see Okay. So, actually, I thought really, really hard about this for a really, really long time, and now you're talking about stuff I did. So, the tangent space of S3 minus K. So the tangent space, and this is the Zariski tangent space of the character variety of S3 minus K into SU2 at any point is the first cohomology of S3 minus K with coefficients in the add of the representation. Now, what I'd rather do is somebody just said, well, you can do it with a manifold with boundary. I'd rather work with a manifold with boundary. And so M is going to be lying in S3 minus K, and that's a compact manifold. And the boundary of M is a torus, okay? And then what I want to do is look at the long exact sequence corresponding to M rel its boundary. And now I'm going to look at it in homology, but that's okay because the dual of the first homology, I'll do it in cohomology. Okay, I'm going to look at the long exact sequence. I just have to get my head together to do it. So here is H1 of the torus, which is the boundary. And then this is H2 of M rel boundary of M. There's add row, add row, like this. And then this is pullback to H1 of M rel add row. Okay. Boy. What's going on? That's H1 of M add row. And this is H2 of M boundary M add row. And this is the restriction map. And now this is the tangent space to the character variety of the knot complement. So that's the tangent space at row of the character variety of the knot complement. This is the tangent space at row of the character variety of the torus. And well, we don't have to interpret this as a tangent space, but this is isomorphic to that by Serre duality, right? And that means that this map and this map are adjoints, which means that the rank of the image of this map is equal, well, they both have the same rank, and the dimension of the tangent space of the representations of the torus into SU2 is 2-dimensional, and that means the image of this map is 1-dimensional. And in fact, that's the argument for why the A polynomial, describes a curve. That's why the restriction of the SU2 representations of a knot complement to the boundary describe a curve, and that's because generically the tangent space is one-dimensional, and it fails to be one-dimensional only at singularities. That good?
This is a little bit to the side, but does anybody know whether any of these SU2 representations are on Thurston's canonical curve?
You know, there are tons of this has been worked to death, and I am sure they are, and I'll tell you why I'm sure they are, because there's only one component for the figure 8 knot.
Yeah, for the figure 8.
And then they're on there, okay. But in general, is every component going to have SU2 reps on it? Yes, and in fact, that's how Nathan Dunfield and Stavros proved that every non-trivial knot has a non-trivial apophthegm. Okay, so
They just need the fact that there is one component.
the one component, right? But they took the canonical component. That was, I think.
That's not done.
What?
But it's not done that they're up to not component.
They're not. It's not. It's just some one component.
Right, I
does
mean,
it.
Kronheimer and Rourke, they tell you they're somewhere.
They're somewhere. Yeah.
It's just Gates theory, though.
Right.
You have no idea if it's definitions of.
You're right. So it's not necessarily canonical.
Don't discourage me.
So.
It's a conjecture.
Come on.
It's a conjecture.
But that's why I want to know if he knows. If you maybe had a different way to do this.
Yeah.
Schoenberg isn't showing his full hand.
No.
Obviously not.
I
Anybody
thought
else
maybe you knew something.
want to ask me a hard question? I can just answer questions if you want. Yes, Al. This is going to be hard,
It
guys.
will be worse because it's not a question but a comment.
Let's hear it.
But that's, of course, what you said is generally true, but we expect it to be true, perhaps. Sort of
Right,
intuitive.
generically, it's true.
But it's not true that the projection of the character variety of manifold into the character variety of the bundle it must have Lagrangian.
Must have what?
Must have Lagrangian subspace. And the reason for that is this whole big problem of important elements. So it could be a subset of Lagrangian subspace. So it's not true.
No. You're just making stuff up now.
Well, the reason for that is when you say that tangent space of character variety is H1.
That's right. Sometimes it isn't. Sometimes it's larger. Right.
But no, but sometimes it's also smaller because really that X should be an algebraic scheme which take a new potence. So it can be also small. But
So I had this. So there's a holomorphic section. There's a holomorphic function on the character variety, so that the imaginary part, so that the real part is the Chern-Simons invariant, and the imaginary part is the hyperbolic volume of the representation plus the length of the shortest geodesic on the boundary. And then the volume, now what I want to say is that essentially the volume being 0 and the length of the shortest geodesic being 0 on the boundary then causes, at least generically, the Chern-Simons invariant to be a local parameter on the SU2 character variety. And so then it does actually, away from singularities, it will continue to it can progress. Otherwise, you're going to violate the maximum principle for a holomorphic function. Okay, it's just like when you look at, you set the imaginary part equal to 0 on the complex plane. Well, there's this whole axis you could move along, and that's exactly the phenomenon. And so I don't think what you're saying can happen except perhaps at isolated points.
Well, if you know a reference, let me know.
There was another part of the story, but let's face it, this was already rough enough, wasn't it?
No, keep going.
You really want me to keep going?
Yeah.
How does everybody feel? You want me to talk a little bit more? Okay, just a little more. So the last thing I want to talk about is the volume on character varieties being right vector torsion. Okay. And I'm just going to stick to a surface group, and the reference for this is Bill Goldman's the symplectic nature of the fundamental group. So here, G is going to be, algebraic, and it's going to be semi-simple, which then means that you've got this killing form, which is non-degenerate and added invariant. Okay. And then we're going to look at a surface of genus G, and as traditional on a surface of genus G, you can work with the standard basis. And so the fundamental group of the surface of genus G that has generators A1 to AG, B1 to BG, and then a relator, which is A1 B1 times A2 B2 up to AG BG equals 1. And now what we want to do is we want to understand the representations of the surface into G. Well, actually, if we take the free group on 2G generators, then there's a homomorphism down to the fundamental group of the surface. And the idea is any representation of the surface gives rise to a representation of the free group. And so what we can do then is we can take the Cartesian product of 2G copies of G, and that's just the representations of the free group on 2G generators into G, because there are no relations. You just choose 2G matrices. And then we have a map from there to G, which then takes A1 to AG, B1 to BG to the product of their commutators. And now the representations of pi1 of sigma G into G is del inverse of the identity. And the problem, of course, is that the derivative of delta is not always onto, but it's pretty easy to ascertain that, in fact, it's onto if and only if the representation is irreducible. And so then you restrict to the irreducible representations. And that's actually a manifold. So how do you go about placing a volume form on that manifold? So you might as well assume that you've got some bi-invariant measure on these and on G, and that gives you a measure on those. And then what you can do is you can take the tangent spaces, and you might as well just identify the tangent space at any A of G with the tangent space at the identity of G by left translation. And now the derivative of delta can be understood as a map from here to here. And then line in here is the tangent space at your particular row of the representations of pi1 of sigma G into G. It lies in there. And there's a short exact sequence. You got a volume form on here, you got a volume form on here, and it forces the volume form on there. And so there's you force the volume. Now, the problem is that you really want a volume on the character variety, and because we're working with irreducible representations, the action by conjugation is pretty well behaved. So then there's an action of G on the irreducible representations of pi1 of sigma G into G by conjugation.
Sorry, I missed what you said earlier. What was the rep I?
irreducible.
Irreducible. The other question was, did you say this D map is always a submersion?
No, I said it's a submersion exactly when they're irreducible.
Oh, I see.
In fact, basically, what happens is if there's an invariant subspace, you can show that allows you to restrict the range of delta, and it's not on 2. So that's exactly what's going on. So this is the action, so you have the matrix here, and it's acting on A1 through AG, B1 through BG by just conjugating, each one of the factors. Like that. So then you take the derivative of that, and that gives you a map, G, and this is the derivative of the conjugation map into the tangent space at rho of the irreducible representations of pi 1 of sigma G into G. And then this goes to the tangent space, the equivalent of rho of the character variety of the irreducible representations of pi 1 of sigma G into G like this. And now you've got a volume here, you've got a volume here, and that forces a volume there. And then that volume is exactly the Reidemeister torsion of the following complex. You just take Ci of sigma G with coefficients in add of rho, and so there'll be C2 sigma G add rho, the boundary operator, C1 of sigma G add rho, boundary operator, C0 of sigma G add rho. Now it turns out that we're in an irreducible representation, so H2 of sigma G with coefficients in add of rho, and H0 of sigma G with coefficients in add of rho are both 0. That's because the covariants are trivial, and by duality, that's isomorphic to this. And so the homology is concentrated in this dimension, but that is the tangent space at rho of the character variety of the representations of this group. And now Reidemeister torsion from this chain complex induces a volume on there, and that was exactly the volume from over there. So in fact, the volume on the character variety of a surface is Reidemeister torsion. There's a similar construction for knot complements due to Jerome Dubois that involves you have to cut down the homology a little bit, and that defines a volume form on the character variety of the knot complement, and that volume form appears in the asymptotics of the colored Jones polynomials, and there's a paper by Kashayev and Dubois that covers that.